Recording. Okay, so good evening, everyone. Welcome back to second lesson of week 17, the first week of database. Explaining machine learning models with the model explainers coding dojo. Announcements. Reach out on Discord if you get stuck. This is a channel link. And your class or LP function can use on BET exam. You are allowed to use, but it must cite the source. Okay. And function use on assignments allowed, but you should iterate or improve on the function as per requirement. Okay. It's fine if you have already used them in your assignment, but you may be asked to do a small resubmission to make the function more unique. Okay. Because it is going to be your portfolio project. Assignments. So before moving ahead about the announcement of assignments, this is our start schedule. And I would recommend, if before coming to the next class, if you can go through and do the readings about the time series visualization, overhauling matplot default sampling, pandas data reader, that would be great. And web form, plotting data, time series starts, normalizing time series. Okay, this will be very helpful before the live class of next week. So today we are going, we have covered in the last class revisited importances and coefficients. And today we are going to cover up global explanation using the same project and local explanation. And the deadline of assigned submission by Friday 9 a.m. PST. Before moving ahead, let's do a 3-minute breakout room activity. So the link. I will share this link in the chat as well. So this is. All of you need to answer these two questions. Write down the difference between model prediction and model inference. You can write down in a one line. Okay? You don't need to dive into deep. What is the major difference between coefficient importance and feature importance? You need to note down the one difference in these as well. So I am going to open a breakout room for 3 minutes. Right. Participating in discussion here. So let's go over the answers. Write down the difference between model prediction and the model inference. Prediction means we set our goal. We care about the prediction. We don't care about what is happening inside that. That is something related to black box model, right? But if we talk about the model inference, this means we are interested in looking inside the relationship between the target and the features, right? We want to look inside the model, insides, right? This is correct answer. And what is the major difference between coefficient importance and feature importance? This is the answer is this one correct. Okay, because coefficient is a value that can be positive and negative, but feature importance is always positive because it is between 0 and 1. We are talking about the feature importance. This means you will not come to know either it's a positive related or negatively. So this is a one and major difference between both of these things. Okay. Okay. Thank you. So we will move ahead. Recap. In the first lesson, you have learned about the difference between glass box model and black box model. What is a coefficient and feature importance? How to extract the coefficients that we did in the, how you can get the coefficients from preprocessor, from model instance, right? We use the two methods. How to visualize the top and features of the model. That is we talked about the feature importance. Okay. So today's learning objective. What is a permutation importance? Why we use it? What are a model explainers? And we will talk about global explanation and local explanation. Okay. So let's start with the why coefficients and feature importance aren't enough, which we did in the first lesson. Okay. Here I would like to give you one example. If all of you remember, you did this lesson data science ethics in AML, right? So in this, you read about this article. For the University of Texas, they made one program that is the grade for machine learning sport for graduate admissions. So in this, it is when they build it, it helps the university to get a more and more student, and admission rate like increases gradually. So this was their model, but it's something went wrong. Because of that, they stopped this model. Okay, the reason behind that, the grade creators were saying it is not programmed to bias between the gender and the face. They were saying we did not make a model which is doing the biasness based on the gender or face or religion or something, right? But the detractors have countered this. They are arguing race and gender can be encoded into other features. They were saying they are not using direct biasness features like the gender. They are not talking about the gender or face, but they are asking, they have the other features like women's colleges, historically black universities. They are using something features like that, right? And letter of recommendation are also known to reflect the gender biasness, because the recommenders are more likely to describe the female student as a caring. So they came to know, rather than using the assertive and these words for the recommendation letter. So this means it is like they were saying this is the biased model, right? And they are not giving the admission to the like the women's from the women colleges and historically black universities. Okay, so that's why they stopped this model. Okay, so that's why this example I am giving here, it is telling you, if you are looking for the feature importance and the coefficient like the importance, it is not enough, right? You need to dive more with the model. So let's start with the permutation. What is a permutation? Why we use it? Permutation importance helps to detect which feature in our data set have a higher predictive power. Okay, but how you can apply it, it's a totally different from feature importance. Now look at it's like it's a process. Why you use it? Because sometime, as we have seen, feature importance is not clear. Maybe it's a like biased by model. Coefficient importance is not enough. In that case, you will use the permutation importance because it is not biased, okay, based on the features. How it works? It is very simple. If you look at this table here, features x1, x2, x3, okay, and this is the your true value, actual value, right? And this is the predicted by your model. And in the third column, we are calculating the error, right? What is the difference between your actual and predicted value? So in this is original order. But when I will apply the permutation importance on this using my Python code, How it works? This is permutation works on the iterative, like iteration based. It's an iterative process. What it will do, it will pick up your one feature at a time. Okay, let's suppose X1. So it will shuffle it. So what will happen? When it will shuffle it, it will break the relationship with your other features, right? And whatever the here predicted value and this one, it will affect this error, right? When you do the total error here, if you look at these, the total error is 1.06, but it become more or larger in this case, right? So this means when I applied on these, the X1 or the permutation importance on these, it shuffle it, it breaks the relationship. It is telling you how important this feature was, how much contribution or prediction power of this feature, which is like for the model, and how important this feature for your model. We will dive deep into the multiple cases in these. Look at this. So this is the first case, right? And now we will jump for the second case here. So here, what is happening? Then after applying the shuffling on the first feature, when I will, like it will goes to the second feature, it will reshuffle it into original order. Okay, the feature which it has shuffled previously. So it will shuffle this. Now again, it will calculate the error. Okay, now it will tell you how important the X2 feature for the model. Right? And if we look at these, the error is little decreased, right? Earlier it was 1.39, it's a 120 here. Now the same process will be applied on X3. Okay, so this is here. So permutation process is iterative process. You can set here how many times you want to shuffle the features and how many features you want, and you can also decide the number of features in this on which you want to apply. Okay, now look at the result. Original order was this, MAE was 1.06. Okay, but when it shuffled the X1, the error was here 1.39, right? And when it is shuffled the X2, it error was 1.20. But when it shuffled the X3 feature, the error goes up more than the previous two. So we are ranking it first. This is the second one and third. So it is clearly telling you X1 feature has the highest predictive power for the model, right? Because error is increasing very high when we are breaking the relationship of this feature with the other. Okay, this is the process how your permutation importance works, how you will come to know which feature is important for your model. Now we will talk about the difference of feature importance and permutation importance. Data used to calculate the important values. In case of permutation importance, you can apply it on test data as well. But feature importance only and only for your training data. This is the one difference. Okay. And biases is in the types, categorical versus numerical. Permutation importance will avoid the biasness, but your feature importance may bring the biasness, because feature importance gives the weightage according to the magnitude of your numbers sometime. So it becomes biased. If we talk about the, like here, let's say the any numeric value, let's say the kilometers, if we are talking about any other numbers, which is like values increasing 2, 3, 4, 5, 6, right? In this case. So biases is in the correlated feature. Only the disadvantage of permutation importance is when your two features are correlated to each other, right? And when it apply the shuffling on the same feature, right? The two features which is correlated. So if you remove the one feature, right? It will decrease the predictive power, because it is tough to like manage if your features are correlated to each other, right? So this is the only, it's a difference here. Feature importance does not have anything. It was about the permutation importance. Definition, difference, what is the process of your permutation importance? What questions do you have about it? Does it make difference? Does it make sense? What is the difference between permutation, feature, coefficients? If anyone have any question, they can type in the chat and we can also discuss after class as well. Okay, take your time. What is a model explainer? Why we need it, right? In previous lesson, I talked about glass box model, your black box model. Today, I'm saying model explainer. Model explainer is introducing itself because word is saying if I want to explain my model, I want to interpret my model, right? This is very important. Why you need it? Because you are preparing the models for very the real-time examples, which is involving death, life situations like healthcare models, right? Credit lending, laws. So these kind of models should be very, very accurate. I'm not saying it is going to be 100% accurate, but we cannot take a too much risk in this. We need to see inside the model, right? And model explainer is critical for food and drug departments as well. Okay. So that's why this is very important. That's why we use it. So way to interpret the model, we have two ways: global, local. Global means you are going to look on the entire data set. Okay. You are going to interpret the model based on the features and given the entire data set, right? But local interpretation means if you are interested in the single data point, if you want to look for the single data point, what is happening with this, right? And how much it is contributing in my model prediction. Okay. So this is like using global interpretation, we can interpret the complete behavior, as I told, all data set. And it helps in understanding how model makes a decision for the complete structure, right? But your local interpretation, what it will do, it will explain you the single data point of your model. That's why we call it local interpretation, right? It helps to know if the model is ready for deployment. This is right. And it helps in understanding the behavior of the model, right? How, if I give you an example, like if you have a 10 data points, out of these, if you want to look for the data point second and third, you want to see how it is like behaving with the first data point and the other data points. That is called the local interpretation, right? If you are removing it, if you are adding it, yeah, or you are shuffling it somewhere like that. This is like example of global, like if you are predicting the disease risk in the patient, right? But if you want to predict why patient has a high risk of disease, you are not only predicting, you are diving inside it. Okay. So this is the difference. So which tools we use for this? SHAP and Line, very popular library. Okay. We use it. SHAP is used for global and local both explanation. It is not only for global. Okay. But Line is especially for local explanation. So we are going to discuss it both today. First, we will start with the SHAP. SHAP full form is Shapley Additive Explanation. Okay. Most important vocabulary term in the SHAP is Shapley values. Okay. So in this, SHAP package applies the concept of from the game theory. We call it marginal contribution. Okay. Like I will give you a very good example in upcoming slides. Okay. So this is a top level definition. Like for example, if you are playing a game, you are a team member of 3 or 4, you want to know how much contribution at the end of the game from the each player. That's why we name it a game theory, because we are going to look for the credit for the each player in the game, right? Because at the end of the game, you are going to win, right, as a team. Okay. So this is called the SHAP. Okay. I will give you a layman example first here. It will help you to make a good understanding about it. Look at this. These are the three friends, Maria, Bob, and Alice, right? They go to the restaurant and they ordered some food and ice cream. Okay. So we can take it as a three features. Okay. Now, what they did when they placed the first order, right? While sitting there, Maria contribute or maybe she eat about of $10, right? Bob eat nothing. He was busy in talk. So Alice ate $20, right? So it is showing the contribution of from the each feature. And then so on in the second time when they place the order. So Maria eat about $15 and then Bob $5, $10 and so on. So I have made the three cases. Now what we say here? Now what is the Shapley value for Maria, Bob and Alice each? Okay. When I am talking about the Shap, we need to calculate the Shap values and we call it Shapley values. And when I am saying the Shapley values, you need to calculate the marginal average contribution from each feature, each player, right? So now we will calculate the average of marginal contribution based on first feature, that is Maria. How we will do that? $10 plus $15 plus $10, right? It's a $25. And then Bob and then Alice, right? So we are looking at it, how much they need to pay at the end of the three friends when they are going to pay the bill. Maria will contribute $25, Bob will contribute $20, and Alice will contribute $35 in the total bill. Okay. So this is, I have calculated the Shapley value in each scenario by the each player. Okay. Now we will take an example here, the baseball batting lineup analogy. This is very popular example of the Shap. So we have a 7 players we need to put together in the batting lineup. These are the 7 players, all are in the same direction, right? Batting direction. And many possible orders with the same 7 player, right? But we will shuffle the order of each player. Like here it is starting with the black player, then green, then purple, right? So we are going to take the 3 cases. When the game starts, now this is a table in which we will calculate the total run by each player. When this is the bases outs, run, total score. So when we talk about the black player, it started, but it did not make any run. It's a here, right? Then we will look at the orange one. It is in the same case, right? Black comes here. This orange will come to here, right? It will be reached to here. And then if we look at the purple one, it goes out, right? It did not make any contribution. And then the blue one, right? Yellow here in this case. But if you look at the yellow one, it takes the round from here. Your orange and black are here, right? So this means it like take 2 runs, right? So your total score will become 2 here by these 2 players, right? And then the green one, no like credit. Here, the red one did nothing, right? So here, the green one, including this one, your total score will become 4 in the first scenario, when the order of your like players are in this case. Now, we will calculate the score in the second case. So this is a green one here. It made the 1 run. So total score is 1. And it made the 0. This is 0, orange, and this one. Now, if you look at the yellow, it made the 2 runs because it completes the 3 players are here, right? So total score is 3 now in the second scenario. Okay. And then we have a third lineup. In this, purple is at the first position, right? Because here the purple is at the first position. This is out, blue is out. Here the HR base is 4, the green one, and the red one made the 1 total. This is also out. It did not make any like run and so on, right? The game is over. So here the total score, if we look at these, this is also 1 at the end of the game. Now in this all 3 scenarios, you have seen we can calculate the run based on the each player, like taken by the each player in this game in 3 different cases, right? So if we converted it into the Shapley values, if we look at this, we can take the where the players are over features, right? We can assume players are over features. We are taking it at the this sign, right? And it will test over many betting orders. So we have tested the 3 betting orders, which are interaction of features are not included in what order. In this, this blue dots in SHAP, blue dots mean it is going towards below 0. Okay. Red means higher value to the prediction. So positive value. Red means positive value, positive prediction using this one SHAP. Okay. So this means this 4th player contribute higher, right? So this feature is contributing in the prediction of your model at out of all these features most of the time, because it is giving you the positive prediction at higher level. So then we can average the Shapley value from each row and calculate it and get a final value for each this one. It will make a more practically in coding understand when we will do the code along. But till so far, what questions do you have about this SHAP theory? All right, take your time. So this is the SHAP usage difference by model. This is very, very important in when you are doing the coding. Okay, your SHAP explainer works based on the different models. Okay, it is not going to use the same instances. If we talk about the random forest, you only need to pass the model instance when you are using the preparing the SHAP explainer. Okay. And if you are using the logistic regression, it will take your in the explainer the instance of the model and your X sharp value. It will take 2 arguments. Okay. And if we talk about the KNN, it will also take your KNN dot predict and the sharp values X. Okay. So this is you need to take care. This is very, very, very important while you are doing the coding. Now we will talk about the SHAP explanation objects, which terms are important in the SHAP. Okay. So first of all, dot values, we know Shapley value is the average marginal contribution by each feature in the model prediction, right? It can be positive, it can be negative. And the base value. So in the base value, what is that? For regression, it is the mean of your white range. And for classification, it is the predict proba, mean of the probability, right? And dot data means original feature from your X data. Okay, so these 3 objects you are going to use. Now look at this. This is a single observation value. If I'm using the 0 here, this is a local one explanation because I am taking out the data from the 0 position index. Okay. And this is showing dot values. These are the values. This is a base value. Okay. This means this is a mean of its a regression model. It's a mean of the white range. And this is the original features data. Okay. Now SHAP summary plot. How would you interpret it? It, as I told, right? This is a summary plot in this. For each feature original, blue means smallest value. As I mentioned, right? Negative, smaller. And largest means positive, right? Higher prediction power. Now look at this graph. This is an example of the house sale price. This is on the x-axis, you have this is 0, mean, right? And this is SHAP values, which we have calculated based on the each feature contribution. If you look at these blue dots, square foot living, it is going on the right side of your 0, negative sharp value. So this means if the square foot living is increasing, your house sale price is going, sorry, square foot living is decreasing, your house sale price is also going to be down, right? Because it is negative, right? And if your square foot living is increasing on the right side, the red dots are increasing on this, your sharp value is also increasing, your prediction power is going high, and the more the house sale price. Year build, this is very important. Year build, if you look at this, if the, right, and in this case, recent one, okay, age of the house is most recent one, like 2022, 2023, then in that case, your house sale price will be decreased, okay? But if your this age is, year built is increasing, 2022, 2023, but if it is decreasing, like if I talk about 1990, 1993, 1995, your house sale price will increase, okay? So this is what these dots are saying here. And same, you need to interpret the bathrooms, what it is doing, how much contribution your model is using, how many times the bathroom is giving the like contribution, blue one. If the number of bathrooms, we can see the red dots as well. If the number of bathroom is here, the smallest value, it is decreasing, the house sale price is also decreasing. But somewhere we can also see the red dot here, right? If it is increasing, in that case also it is, the price is decreasing because sharp value is decreasing, okay? In the like prediction of the house sale price is decreasing. And here is the floor, right? On the right side, this is the red one, it is increasing, largest value. So the number of floors are increasing, price of the house is also increasing, prediction power is higher in that case. Number of bedrooms, again, if it is increasing, price is decreasing, okay? But some data points in the blue is on the right side and red is also there, right? So this means if smaller number, if a house has a smaller number of bedrooms, sometimes its price is also high, okay? So this is a way how you will interpret the sharp summary plot. And this interpretation is most important. This is the one of your BET rubric part, okay? You need to interpret the results very clearly in BET exam, okay? So this is very important. What questions do you have about its interpretation?
So if the SHAP value is in the negatives, does that still mean it has an impact? It's just like the opposite of the positive?
Yes.
Okay, great.
Yes. It is helping the model, but in a negative, but model is not able to predict at a higher positive value, negative value, in negative.
Okay.
Value.
So is it kind of similar to like correlation, like a negative correlation versus a positive correlation, or is that not?
No,
right?
We are not talking about here correlation. We are just talking about like this your waterfront bedroom and other features are used by model, right? And how much negatively or positively it is contributing. Like you can say if number of bedrooms, we can see the it is also here increasing on the right side, but in the opposite direction, right? Negative value is increasing. So number of bedrooms will increase, then your price of the house will decrease. But correlation is something when you are talking about the, it is not like something like we are saying the prediction power, we are just talking about the coefficient relationship with the target, negative or positive.
Okay, got it.
But here we are talking about prediction power.
Thanks.
Now I have a 2-minute break room activity. Okay. In this, although I have explained about the bathroom and floors, bedrooms, okay, so I will open a breakout room for 2 minutes. All of you can think or discuss about how would you explain about waterfront. Okay, our interpretation of waterfront here. Okay, if anybody have any question before I open a breakout room, they can ask. Hey, Joseph.
Sorry, I'm back. I was in the restroom. Are we in breakout rooms right
Okay.
now?
No, every student is coming.
Oh, did I miss it? Sorry.
Yeah,
I actually wasn't. So
yeah. Anyone from room 1 can interpret it about the waterfront? Or maybe from room 2? Mm-hmm.
could you ask that question again, please?
Yes, Joseph.
Thank you.
The question was waterfront. How would you interpret the summary plot or the waterfront feature in this? How it is contributing in the model prediction?
I was thinking that the lower feature values in that feature aren't contributing very much, but the higher one, or at least one of the points, was contributing more to the model.
Yes, but we will say here word like waterfront. We whenever we are interpreting it, right? You are saying correct, but I will do the more addition in this technically. So in the waterfront feature has a 0, like no negative sharp values, right? So it is not like have a negative prediction power with the model, but it has a sharp value positive that is between here, we can say, right? So it is a helping in the higher prediction like this way. We will use the term sharp value of the feature, not along the word feature. Okay. So it will help you to interpret and also improve your skills technically if you be very specific. Okay, good. Anybody have any question before I move ahead?
Okay, I still did not follow that. I did not understand the words. Don't laugh at me, Joseph. Don't. I saw that.
Okay.
I was gonna say it's pretty. This is pretty hard. I was having a hard time following it too.
Yeah,
Okay, so we still don't understand.
okay. So for example, let's take an example of square foot living feature, right? Square foot in the shape, your blue dots for the smallest value. This means negative. It can be on the right side. It can be on the left. Sorry, it can be on the right. It can be on the this side. We will say it smallest value. When it is on the right side, it becomes negative. Okay, because this is on the 0 of other side. But if it is coming on the right side, it's a positive. Okay, still it here it is a value, sharp value is increasing, right? But your this year bit, sorry, first I will give this square foot living in this, smaller the square foot area, negative square foot living area, prediction power is negative. No, like the house sale price prediction, right? If there is a no square foot living of the house, how we will decide the price? right? But in SHAP, red color belongs to higher value. Okay, it is if it is on the right, like the right side of the this your zero here, right? It is positive. It is on the, if it is on the left side of the zero, it is negative. Okay, because this is a zero, this is negative portion, this is positive portion. So now we know red dots belongs to the highest value. So this means if a higher the range of the square foot living area, the house sale price will be high. If a area of the house is 2000 square feet, the price of the house will be $5 lakh. If the square foot living area is 10 square foot, the house price is nothing, right? It's a negative. So it's a prediction power is like contributing in this negatively, we will say. Okay. If we talk about here year built, this is in the opposite direction. If you look at it here, year built, the red dots, which we are considering the higher value, right? In year, if I'm talking about the higher value, I'm talking about the most recent year, right? Above 2000, maybe about 2015, 16, 17, 23. So this means recent age of the house, more new house means it's a cheaper, right? It's a cheap house, right? Its value is less. Okay, but if a year built here, the age is small. If a house age is like 20 years old, 15 years old, 30 years old, its price is very high. Okay, so this is how you need to interpret it. First, you need to look at it. X-axis, this is your zero. If it is coming on the left side of this, this is negative value. It is coming on the right side, this is positive value. And but your red color belongs to high positive, highest value, and blue becomes the small value. Okay, it is positive or negative. This you can decide after looking at the graph. Okay, did I answer your question? If still there is any confusion, we can discuss it after class again. Okay, shall I move ahead? I will explain it again after class. Okay, don't worry about that. So this is, we are talking about the global SHAP explanation. Okay, now we will talk about the local explanation. Local explanation means you are going to focus on the one data point at a time. Okay, how it is reacting with the neighbor one data point. Okay, now look at this. Let's get a local explanation for house that has many bedrooms. We are going to talk about the number of bedrooms, how this is affecting a single data point, right? We are considering here bedroom, one data point from it. Okay, so here we have plot the force plot here. Now how you interpret this? This is the graph. Again, the red means higher contribution, largest value, and blue means smallest value, right? In this, if you look at this is your predicted value, okay? And this is your base value. This is the mean of your white range, okay? And in this, we can see, but if one data point, we are taking the values. If in this, let's say at some index point, one data point where the number of bathrooms are 4, square foot living area is 2,690, year built is 9060, bedrooms are number of 7, floor is 1, the price is this predicted by your model, right? And we can clearly see here which feature is contributing lot in higher prediction of the house positively, right? We can see if number of bathroom is 4, area is large, house price is higher, right? On the other way, this is your year belt is smaller, right? It is on the your sharp value may be negative, but still it is contributing in higher prediction, and it forces these two features are forces to give it a higher prediction here, right? So this is how you will interpret this your sharp force plot. This is for the single data point values. What are the values and how it is contributing in the higher prediction or maybe the lower prediction. This is the example of higher prediction. What questions do you have? All right. So we will move ahead. Now we will talk about the local interpretable model agnostic explanation. That is a line. This is only and only used for local explanation, not for global explanation. Okay. So it is, it can explain many types of model. That is maybe your data has your model is in the tabular data form, text classification, image classification. Okay. You can apply it, apply this on any model. Now, how it look like? Here, we will create a tabular explainer with training data and features name. Okay. Here, we will consider again only one row, one data point. That's it. Okay. Now, look at this. Here, it will give you some negative to positive range. This is your original feature. Okay. And this is the value of those one. But when you apply the line on that, it will show you how it is contributing in prediction. This is on the left side again, right? This is negative. On the right side, this is positive. And if square foot living area is again increasing, house sale price is this one, right? And waterfront here, this is a less than is equals to 0, right? This is showing this much price. And then between 1949 or maybe some range is here, right? This is the price. So in this case, this is negatively contributing. In force plot, we have also seen it is negatively contributing, right? But still the price is high. And this is the floor showing negatively what is the range of the floor if it is equal to less than or equal to 1 floor. Okay. And number of bedroom if number of bedroom is greater than 4. Okay. So it is showing you the local data point with its original value, right? And you can clearly see how it is affecting your prediction, right? So in this case, we can say if here most big contribution is a square foot living, waterfront and bathrooms, right? But as a layman, sometimes we think if the number of bedrooms will be larger, the price will automatically large as a layman. But model is something saying something else, right? So this is the advantage of if you want to dive inside more your specific data point of the model. Okay. Now, what questions do you have? Right. I will show you at this picture of the line here. Here you can see this is the global, this is non-linear relationship, right? Non-linear data. So you can see here many points, right? But I am only interested to look for this data point, the larger one, how it is coming on this line. Okay. So when you apply the line, it will look like this. It will focus only on this data point. Okay. So this is like for the visually example of your line. Okay. How it will do that, how it is making the predictions, right? You will come to know in detail when you will apply the line on this. Now, before I jump on to the your code along. If anybody have any question, please feel free to ask.
So global explanations are just in the summary plot?
Summary plot we use for the global explanation, right? It is not something like we will say it is related to your global explanation, right? It is just the graphical representation, okay, for the SHAP.
So how can you distinguish between what's a global explanation and what's a local explanation?
Local explanation, you are plotting the either this graph explainer using the line, right? And this is for the force plot.
I got that, but what's the difference? I mean, why make a distinction? If we're not using global explanation for anything, then why are we talking about it? That's what I'm trying to get at.
For global explanation, you will use a summary plot. This is a
That's what I
global
was thinking.
Yeah, it is a summary plot. This is for global and this is for your local force plot, single data point. Okay, and for line, you use this one, explainer. Okay, so this is the difference. Right, this is a link of the main repository and this is a code along and this is open at my local place. So we are going to use the life expectancy which we have used in the same first lesson, right? In this, I will not like explain again this code because we already did in the last class. So this is the import part. This is our evaluation custom function. And here I have made the importance function, custom one, and plot importance, which we did in the last lesson as well. This is here, we will start from here. So we saved the model last time using the job lib. It's a time to use the same model to do the further, like the model explainer for the, apply the model explainer. So first of all, we will put your model. So you will define the name which from in which folder at local place you saved it. You will load it. These are the keys we saved last time. Okay. And then you will separate it into the separate variables here. Okay. Using this because it's a dictionary, we will separate it in this form. Okay. Now, when I want to look at it, I have my X-train, my model, my preprocessor, everything. If I want to evaluate it, when I ran it, this function evaluate regression by passing my parameters, it gave me this error. String to float, developing. Can anybody tell me why this error is coming and how I can fix this? This is the most common error which we face, come. I will give a hint. Like it is a saying, could not convert string to float. Over machine only understand the numbers, right? When I am trying to evaluate it, I am passing something feature which is not already converted. It is still categorical. So how would you fix it?
Would you like one hot encode it?
Yes, Joseph, correct, right? We will convert our categorical into numerical. Great answer. So we will load it. We can see here status is coming in the form of developing, right? So now here we will create it again because I need to convert it into one hot encoder. So we will get this method again we are using here to get the name of the features, right? We will transform the data here, train and test, and then it is converted now. If we status developing, it should be coming on this side, right? This is converted. Okay. So now we will evaluate it again. Now it is running fine. Okay, it is showing me this score, it's working fine. So if you have a like large number of after decimal, you can format it like this way. Either it's a coefficient value, either it's any number. Okay, this is a way how you can handle them. Now it is the coefficients here. If we get the coefficients, we can see the year coefficient value is 0.03, right? And then infant death is this. Now we will move ahead. This is the linear regression coefficient graph, which we did in the last lesson, okay? Which is positively contributing in your prediction, which is negatively, okay? So now we will evaluate using the random forest and we will plot the feature importance, okay? It is showing you the top 5 or top 10 features which is contributing in the model prediction, okay? High impact of these features on your model. Okay, it is not telling you positive and negative relation, it's only positive impact. Now, today's our goal is talking about the permutation importance first. Okay, so in this, you need to first import the package sklearn inspection, import permutation importance. Okay, when you import it, after that, we will apply the permutation importance on random forest. Okay, so this is the method permutation importance. You need to pass your first instance of the model, your test data. As we know, you can apply the permutation importance on test data as well. Okay, and this is your predicted scoring R2 and number of jobs is equal to 1. Here, the number of jobs is equals to -1. Okay. Why I have passed it -1? Because the permutation process takes too much computational power. Okay, so I want this method use my all like parallel in parallel the all server or computation power. Okay, so it process the things very fast. That's why I'm not giving any number here. I just mentioned it -1. But if you mentioned it here 2 or any 1 or numbers, then it will take time. Okay, so now when I did it, okay, so this is the result keys. It is just we are printing what it is calculating. Okay, now when I applied the permutation importance, we will print it into this form. Now look at this. How much year is contributing in your model? 0.01. Okay, the second number is coming 0.02, right? Which number here, if we say contributing or affecting a lot when I shuffled it, okay? Because we are calculating here mean absolute here R square. This is an error, right? So it is showing you this is all errors of the each when you are shuffling each feature one by one, showing the result of that one. Now we will plot it in a graph. Look at this. This is the permutation importance based on your error. After shuffling, after breaking the one feature relationship with the others one. Okay. When it shuffle the HIV/AIDS, it break the relationship with the other, its error is going to be very high. This is 0.44. Okay, so that's why in the graph it is coming at the top. So this means this is very important for your model in prediction. It is impacting a lot when we are shuffling its data point and breaking the relationship with the other features. And same again, at the second number, it's a composition of the resources. Okay, Joseph, do you have any question?
Yeah, I think I'm not understanding what the numbers mean in this scenario. Like, what does the 0.44 mean? Does it mean it explains like 44% of the model, or?
In case of percentage?
Yes, is that what that's saying essentially?
Okay, you are asking, your question is in case of permutation importance, what it is telling us?
Yeah, what does the number mean? Like, is that how much it moved the mean, or is that how much it explained the model as a percentage?
How much model explain the not that percentage? It is telling you if you are shuffling the feature, after shuffling, when it will break the relationship with the other features, how much it is impacting your model. Because look at this, if I say HIV AIDS, right? If when I applied the permutation importance on my this data points, when I shuffle the HIV AIDS, it is increasing the error of your model. Okay, so higher, this is like all the MAE will be the your average error of all the one, right? So this means this is impacting lot your model. We are just telling how much contribution is important of this feature in the model.
So is it 44% important or is it increasing by 0.44? Do you understand my question?
No, this is the error.
Oh,
Remember,
okay.
I show in the Excel sheet when we are talking about the error produced, if we are shuffling the each your that one, look at this. This is the importances of the mean. So what method I have applied here? R square. Okay. When it is calculated, it will show you the results of importances underscore mean. This is a mean absolute error based on the shuffling of each feature at the end. Like this. I show you in the slide. Maybe it
Yeah,
will
sure.
make, yeah, here we go. This one. This is here. Look at this. When I shuffle, let's suppose you can take the HIV AIDS X3 here. This is the HIV AIDS.
Okay.
When your permutation importance shuffled it, your error goes up. This one.
So it goes up by 0.44.
Yes. Right?
Okay, that's my question. Thank you.
Yeah.
Okay.
Right?
Yeah,
So
no, I understand now. Okay.
yeah. This is a person in the form of at the end. That's why it is showing the importances underscore mean. Right? This is a standard deviation and importances, and we are
I think I was confused because they look at percentages, before he times 100, right? They kind of like percentages in me. So I think that's why I was confused. Thank you though.
So this is showing the permutation importance of each feature when we are shuffling it. Okay. Now this is a permutation. This is a feature importance. Now, if you want, you can do the comparison. In case of permutation importance, you have a HIV/AIDS, income composition, under 5 deaths, thinness, infant deaths. But here you have schooling before the thinness 9 years. So we can see here, right? Maybe feature importance is why the feature importance chooses the schooling. It depends, right? Like maybe it's like numerical, maybe get biased toward it. It can be any reason, right? But there is a difference. Schooling is coming very down here, right? According to permutation importance, it is coming down here. Before this, these are the top 5 features which is contributing lot. It is affecting the model lot when we are applying the permutation importance. Okay. And this is the feature importance. So you can explain the model based using different model in like the explainer, and check which one is the good one giving you the result. And now we will talk about the linear regression feature importance. You can use the same method. Okay. So here I added a 1 parameter and repeats is equals to 3. So it will repeat the process 3 times. Okay, on your entire data set. And then look at the result here. Now, when I plot the here, this is not the feature importance, this is the permutation importance, right? And then for the linear regression, it is showing now HIV/AIDS, income composition, under 5 deaths, thinness, infant deaths, right? And this one. Does it make any difference when we have changes the number of the jobs repeats? This is same. And this seems to be same here. I think first 4 or 5 features. Okay. So this is only the difference. I have make it repetition. Okay. That was only one time, but you can repeat this process as much as you want. Now we will talk about the global model explanation. So what is that? As I have mentioned, global explanation means we are going to look inside the entire model by considering entire data set. So in this, we use the SHAP before applying the SHAP. So if I want to apply this global explanation using the SHAP, instead of applying on taking the whole data set, my job is I will pick up some sample to fasten my process. Okay, so that's why we will take the instance of SHAP dot sample x train underscore df. Number of samples we are taking 500. You can increase and decrease. Random state we have set. We will set the x SHAP from x train. Okay, and then because we are picking up some points from our entire data set, so what we will do here, we will do y train location x SHAP dot index. So your y value should match with your x SHAP value. That's why we are using this code here. Okay. Now look at the result. So it is starting from this point and going down random, right? And then you need to declare the explainer SHAP dot explainer method. This is your, we are applying it on the random forest regression. So it only need a one argument, that is the model name. Okay, as I have shown in the slides, different model have a different argument of the explainer. Okay, so now we will say that we will calculate the SHAP values from the explainer. This is X SHAP, Y SHAP, which we have created above. And now we will plot the result. This is a global explanation graph, summary plot. Okay, now look at this. So for each model, if we look at on this, there is a no negative value, right? All are contributing, or SHAP values are positive, right? Now, which one is highly impacting? HIV/AIDS, right? So in this, if HIV/AIDS is increasing, life expectancy rate will decrease, right? Life expectancy, it is contributing more in your model. Okay, in prediction. Income composition of the resources, this is the second one. Under 5 deaths, this is the third one. And then this one, so on. So this is showing you globally which feature is impacting a lot. Okay. And Shapley value, it is telling you how much this is contributing. This is like if you connect it again with the game theory. Now these are the all players, right? So HIV/AIDS player, how much it is contributing with the SHAP value? More than 4, right? And this is the second one, third, fourth. Okay, each feature contribution we can see in the model prediction. Okay, and now look at this. This is a summary plot. Okay, so in this, what you can see here, higher value belongs to your red color. Low value means blue color. Look at this SHAP value here in this summary plot. Here on the left side, it's a negative value, right? On the right side, it's a positive value. Okay, and HIV/AIDS. So this is red means higher value, higher negative value, right? So when it is higher, right, the life expectancy will decrease, right? If it is a low, blue means low value, right? And it is on the right side of the zero, low value, positive value, your life expectancy will be high. Less HIV kids, higher life expectancy rate, right? And income composition of the resources, this is something blue here. So this means negative composition of the resources. What it will do in the prediction of your life expectancy, decrease it. It's a negative. Okay? If it's on the either side, it's a positive in some cases. So it is increasing. Okay. So this is you need to interpret it like this way. Can anybody interpret the year here? How would you interpret the year? This one. How it is contributing?
Wait, what is the year to data set again? Like, what does that column represent? Is that like is that 2012, 2020? Is that what it means? Or is
Yeah,
it,
same way. Like if the one person is 20-year-old, right?
oh, is it
Or
so it's their age essentially? Is that what it is?
yeah,
Okay.
it's a
So so on the right side, if you have higher age, right, your life expectancy decreases. Whereas if you have lower age on the blue on the left side, wait,
okay.
I think am I getting it backwards?
Okay. Okay, I will explain. See,
Yeah,
again,
please.
Red dots means high value. Forget, okay, forget it about negative or positive. Just think red color means highest value. Okay. And blue means lowest value. Okay. These are the two things when we look at the sharp. Okay. Now, the next point come up. How would you decide your value is negative or positive? It can be red, it can be blue. Okay. Red points are on the left side of 0. Value is a high, but it is negative. It is a high in negative. Okay. If it is on the right side, it is still high, but positive way. Okay. Same with the blue. If blue dots is coming on the left side, it is low, but in negative. If it is coming on the right, it is still low, but in positive way. Okay.
How do you interpret alcohol? It seems to be kind of all over the place. With like a strong, like, you know, red on the right, red on the left, a lot of blue in the middle.
This is coming here. Look at this. This is
No,
a
I understand.
sharp.
I'm asking, how do you interpret the feature that's alcohol? It's like in the middle.
Okay. This is contributing like nothing. It is at the 0. Like
Says
it
it's
is
kind of nothing.
not nothing. I will say not higher contribution, right? Because it is not increasing, decreasing. It is just set it at the mean.
Yeah, it's like a little cross formation, which is
Yeah.
weird. It's
Yeah.
just kind of, it's not really doing a lot. It's essentially has a lot of blue in the center and red on the tips. It just looked weird.
Yeah. In this, right? If the age of if the person is older, this is like understood. Age is life expectancy rate is high, right? Because person is older, right? I will explain it after class again. Okay. If still
No,
have
actually, I understand it. I just didn't know what year meant. I was confused about what that data was supposed to be, essentially.
okay. So here we are going to apply it on linear regression now. Okay. So this is a summary plot of your linear regression, right? Like we do in the feature in that this is a mean and sharp value under 5 DATs, infant DAT, schooling. In case of linear regression, earlier we have seen the regression model. But if we go down, look at this. Here under 5 DATs, but this chart is explaining you, is it affecting it in a with the sharp negative way, right? Still, look at this. This is a high value under 5 DATs. If under 5 DATs is increasing, right? It is increasing, but negative, right? So here the blue dots are here, right? So this negatively increasing the value, largest value is in the negative form. So it is affecting your model in negative way in the prediction, right? And infant death, if it is increasing, this is positive, right? Life expectancy will decrease, right? And in these, no, it is increasing. We did it in the last class as well, how it is impacting. This is some value, not all. When we did it in the last class in detail, right? After that, now we will talk about the local explanation of the sharp. This was a global one. You can see the each player contribution, each feature contribution in your model, right? And this is X sharp. This is again, you need to reset index. This is very important part. Whenever you are doing the global explanation, and after that you need to apply the local explanation. Before that, you need to reset index. Otherwise, you will get the errors like out of index or something other things. Okay, this is very important. Okay, so we need to reset it because we picked up the samples before that. Okay, so we will reset the index. and now look at your data. This is coming in the correct form, right? Now we will pick up the infant deaths. I'm interested in how it is affecting, right? As we have seen here. That is in detail. We will come down. So in this, first of all, we will save the index of the most deaths. The data point, the index value of the data point where the most of the count of the infant death is highest. Okay. So we will do that, and then we will allot the index location with this parameter. This is 449 index. So we will got all values of the at that data point of all other features of this. Okay. And then we will check the value of the predicted one, this one 63.7. Now we will plot the force plot. So this is using linear regression. In this, you are passing the explainer underscore linear regression. Expected value means mean value of your this one. Okay. And sharp values, this is you are passing the your high death rates dot values. We did it, so we can access the values at that index. This is feature name. Now look at this force plot. Here we go. Here, this is the infant deaths. When it is 1700, this is the maximum number of the death of the infant in our data set. When the under 5 deaths are this much. Only in that case, this is base value is just is hidden behind this. This is your predicted value. Okay. So this means in this data point, when your infant death is maximum 1700 and under 5 death is also higher, right? In this case, although it is a lower according to your sharp value, right? But it is contributing, both features are contributing at this data point to predict the life expectancy rate higher. Okay. So this is how infant death is contributing a lot in your model because of these values. Okay. When your infant death is 1700, at the same data point, your under 5 death is also a big count. That's why it is predicting the higher life expectancy. Okay. This is a reason. Otherwise, if we look at the graph, it is not making sense to us. In case of higher, if the infant death is increasing, why the life expectancy rate is increasing, right? So this is a life expectancy, your age. This is the rate of that one. Okay. Now we will apply the same using random forest. Same local explanation using different model. So here, this is your your predicted value, and this is HIV/AIDS, right? This is showing you the higher contribution HIV/AIDS, but other contribution of income composition resources, schooling, under 5 deaths, BMI, other features all contributing low. But because of this HIV/AIDS higher contribution at the same combination, the data points, it is increasing your life expectancy rate. Okay. So this is a reason. Graphs, sometimes it make us like wondering why this value is increasing life expectancy, why this value is increasing house sale price. As a layman, which is not possible if we think, right? But we can clearly see inside the model at a specific local explanation how it is helping, including the other features. So it is not the contribution of your one feature. At some data point, it is a contribution of your other features, right? So these are the features forcing it for the higher life expectancy. HIV/AIDS forcing from this side, higher, largest value. Okay. Now we will talk about the line here. This is only used for local explanation. Lime, you need to import the package lime.lime_tabular lime tabular explainer. Okay. So you will create the tabular explainer here, and then training data xsharp local values. Okay. This one. Then xsharp local columns, and then mode is regression. in this. Okay. And then Lime Explainer is ready. So we will use the Lime Explainer .explain instance to plot our graph, to look at graphically. So here, this is your, we are again looking at the same data point of your infant deaths. Okay. Now you need to pass here these parameters. This is your random forest regression .predict. Okay. Now you need to say show in a notebook. If you want to look for this graph, you need to add this line, show in notebook. Okay. Sorry. So this is your predicted value range, minimum, maximum. Okay. 50.18 to 83.49. We are at this value, 63.47. And this is your actual values, actual features. Now look at this. Your range of the HIV AIDS between 0.10 to other. This is not, the range is coming here, right? So this is like helping your, this feature, if we look at this specific value, this values between this range is helping in higher life expectancy prediction by the model. Okay. But at the same time, measles, this is also contributing little bit with the HIV/AIDS. It is forcing the model to do the higher prediction, including the negative force of the other features, income composition, schooling, under 5 death, BMI, and so on. Okay. So this is the explanation with your own local values, data points, which is forcing the model for the higher prediction. Okay. Now this was all about our today code along. Now anybody have any question? Yeah, Jericho, you can remove it after analysis everything. If you think any feature is not contributing, then you can. Okay, which is not making sense with the model. Welcome. What questions do you have? All right. So now, before closing it, I have this poll for all of you. It will help me. How much did you get from today's lesson? I will repeat the topic if still there is any confusion in the Lyman chat. Okay. 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 So summary of the class is, what is the permutation importance? What are a global and local model explainer? In the next class, we will learn about the introduction to time series, most interesting topic, okay, of the next week. Now I'm going to stop